This video contains the solutions to the double integrals and polar coordinates practice problems. For this first one, we want to compute the volume of the solid below the surface z equals 4 minus x squared minus y squared above the region described in terms of r and theta. Now remember that whenever we want to find the volume of a solid, one of the ways that we can do it is simply by doing a double integral of the top surface minus the bottom surface. So in this case, since I want the surface below that, the solid below that surface and above the region, what I'm really saying is that the bottom of the solid lies on the xy plane. And so let's think about this region here. So the top surface is going to be the z equals that they give us, and the bottom is going to be the 0. So now we need to set up the double integral. So the volume that we're going to want is the double integral over this region R of the function 4 minus x squared minus y squared minus 0 dA. That's the setup. All right, so what's this region look like? So in polar coordinates, we want to go from r equals 1 to 2, and then we want theta to go from pi over 2 to 3 pi over 2. So that's from 90 degrees to 270 degrees, and so the actual region that we want is this region right here. So that's r equals 1 to r equals 2, and then again here's theta equals pi over 2, and here's theta equals 3 pi over 2. So since this is a region that would be very hard to set up in terms of Cartesian coordinates, trying to slice this vertically, we would have a lot of different slicing and have to break it up into several integrals. But this is a polar rectangle. This is going to be a nice integral in polar coordinates. So in polar coordinates, we're going to set this up as the integral from pi over 2 to 3 pi over 2, the integral from 1 to 2 of my function. Now, I don't want to write it in terms of x and y, I want to write it in terms of r and theta. So the nice thing is that 4 minus x squared minus y squared is really just 4 minus the quantity x squared plus y squared. And we know that when we convert back and forth between Cartesian and polar coordinates, x squared plus y squared, that's just r squared. So my function here is r squared. And remember that in polar coordinates, dA is r dr d theta. So my inner integral is with respect to r, my outer integral is with respect to theta. And the dA simply becomes r dr d theta. That's my kind of conversion factor for my little area units in polar coordinates. So we multiply this out and integrate. Pi over 2, 3 pi over 2, integral from 1 to 2. Multiplying that out, we get 4r minus r cubed dr d theta. First integrate with respect to r. We get 2r squared minus 1/4 r to the 4th, evaluated from 1 to 2, d theta. When we plug in and subtract, that works out to be 9/4. And so then we have to integrate from pi over 2 to 3 pi over 2 of 9/4 with respect to theta. That's going to be 9/4 theta, and when we plug in and subtract, we get 9 pi over 4. And that's our result. Very similar problem here. So again, we want the volume of a solid below a surface and above a region. So again, the top of the solid is going to be that surface, and the bottom is just going to be the xy plane. So we're just going to integrate that function over our region. So the volume that we want here is the double integral over this region R of this function 5 minus the square root of 1 plus x squared plus y squared dA. And again, my region is a nice polar rectangle, so while I don't have to do this one in polar coordinates, it's certainly much nicer to do it in polar coordinates. So let's set it up. We usually put the thetas on the outer integral and the r's on the inner integral, but again, it's a nice rectangle, so we could easily switch that up if we wanted to. And then we rewrite our function, again, keeping in mind that x squared plus y squared is nicely written as r squared, and that when we switch to polar coordinates, we get r dr d theta. So now we can realize that to do this integral, we can do a substitution for that inner integral of u equals 1 plus r squared. du is going to be 2r dr, which just means we would need a factor of 2, and we can put a factor of 1/2 out front. So that creates an integral that looks like 1/2, the integral from 0 to 1. So when r equals 0, u is going to equal 1 plus 0 squared, which is 1. And when r equals 1, u will be 1 plus 1 squared, which is 2. So we integrate from 1 to 2. 5 minus the square root of u du d theta. So now we can integrate that. Antiderivative of 5 is 5u. Antiderivative of u, think of u as u to the 1/2, so that's going to be u to the 3/2 multiplied by 2/3. And then again, we need to plug in 1 and 2 and subtract. When we do that, we're going to get 5 times 2 minus 2/3 times 2 to the 3/2, and then minus the quantity, 5 times 1 minus 2/3 times 1 to the 3/2. And then again, we need to integrate that with respect to theta. So 2 to the 3/2, that's 2 radical 2. So this thing right here, this ugliness thing, that's going to be 4 radical 2 divided by 3. Anything 1 raised to any power is just 1, so that's just 2/3. This is 5, this is 10. So that's going to be 17/3 minus 4 radical 2 over 3. And when we integrate that with respect to theta, we just get that stuff times theta, plug in pi, plug in 0, so the whole thing just gets multiplied by pi. So what we end up with is 17 over 6 minus 2 radical 2 over 3, all times pi. It's a little bit nasty looking, but that is the result that we get. So here we just have to set up a generic iterated integral. So we're not actually going to be doing any iterating in this one, we're just going to be doing the setup. And so here we have a region inside a polar curve. And remember that when we read these polar graphs, we want to read them radially. So this here is where theta equals 0. And if I continue to go around, this will be where theta equals pi over 2, theta equals pi, theta equals 3 pi over 2, and then all the way back around to the beginning where theta equals 2 pi. So since I want the region inside this entire curve, my theta is going to go from 0 to 2 pi. Now my radius is going to go from the origin, where r equals 0, all the way out to this curve, 1 plus 1/2 cosine theta. And then I integrate my generic function, f of r theta, and then dA becomes r dr d theta. So that would be my setup for my generic iterated integral. Now when we look at this setup, we want to just evaluate a double integral, and at first glance, this doesn't look like a polar coordinates type of problem. But if we graph this region, we want to know where x squared plus y squared is less than or equal to 9. Well, if x squared plus y squared is equal to 9, what we get is a circle of radius 3 centered at the origin. And we're also told that we want y to be greater than or equal to 0, so that means we're just looking at the upper half of this circle. Now, we could do this integral in Cartesian coordinates, but the problem is that it would be a very nasty integral because the upper bound here, the upper curve, is the curve y equals the square root of 9 minus x squared. And that would be my upper bound on my inner integral, and then I would get an expression that I would then have to integrate with respect to x that would have that expression in it. It's not necessarily impossible, but it would be really nasty. And the good news is that not only is this region a polar rectangle, but the function that I have to integrate, x squared plus y squared, is a nice function that's easy to express in polar coordinates. So this is really a tailor-made example for doing in polar coordinates. So my theta is going to go from theta equals 0 all the way over to theta equals pi. So my outer integral goes from 0 to pi. My r goes from the origin out to my curve, which is r equals 3. Remember, circles are really easy to describe in polar coordinates, especially when they're centered at the origin. So from 0 to 3. And then my function that I'm integrating, x squared plus y squared, that's just r squared. And then dA just becomes r dr d theta. So this is about as easy as double integrals come. So r squared times r, that's r cubed. The antiderivative of r cubed is 1/4 r to the 4th, evaluated from 0 to 3. That gives us 81 over 4. With respect to theta, integrate that, we get 81 over 4 theta, evaluated from 0 to pi, which just gives us 81 pi over 4. And I guarantee you that is way faster than that would have gone if we had tried to do it in rectangular coordinates.